Welcome to the Chapter 11 Study Guide. To measure the wavelength of a wave, you can either go from crest to crest or from trough to trough. Make sure, just as a note, that you do know the different parts of a wave, like crest and trough. You should know those things. But to measure the different wavelengths of these two waves, well, I would mark a dot at the crest, mark a dot at the crest, and draw a line from each of those two and mark it with a wavelength symbol. And I would do the same over here and mark it with a wavelength. Or you could do trough to trough and mark it with a wavelength. What is the relationship between wavelength and frequency? This should be a pretty straightforward question. You can answer this question simply by looking at one of the waves. So I'm going to look at wave A that we just went over. So on wave A, the wavelength of A is fairly large, but the frequency of A is small. The number of times it'll pass a certain point. And it's kind of got that lazy river sort of thing, so the frequency is small. If you look on wave B, the wavelength is small, but the frequency is large. So as wavelength goes up, frequency goes down. We call that indirectly proportional. The relationship between energy and wavelength is exactly the same as that between frequency and wavelength. If I were to ask you, for instance, what about the relationship between, say, frequency and energy, what would you say for that? Well, that one's the same. As frequency goes up, energy goes up, or the other way around. Make sure you know those relationships. This question's asking if you understand the relationship between the colors of light and wavelength. And one of the things that you should know is that red light has a lower energy than blue light. Blue light has a much higher energy. Well, if that's true, that means blue light must have a lower wavelength, and red light then would have a higher wavelength. So if you looked at these two waves, which one would be red? Well, I hope you said A, because that is correct. To answer this question, you have to remember how to find the number of protons and hopefully the number of electrons. Phosphorus has 15 protons. So then it would have, 15 electrons. Good. Yeah, because they have to be the same to be neutral. Okay, well, Rutherford knew that there was this dense, positively charged nucleus. So I'm going to put 15 protons here for the nucleus. Where did Rutherford say the electrons were? Yeah, he didn't have a clue. The electrons were just out here, any old where, somewhere in this space. You don't really need to draw all 15 electrons if you actually write down the words that, yes, they were all 15 in this space somewhere around the dense nucleus. Bohr had some very specific ideas about where those electrons were located. Number one, yes, 15 protons in the nucleus of the atom. And then he had a first set energy level, and this first energy level should be drawn in a circle. That's a really bad circle, but that's okay. And he said 2 electrons can fit in that first energy level. And then we have a second energy level. How many electrons fit there? 8, that's correct. 8 electrons. Then we have a third energy level. How many electrons? 18. Oh, but we don't need 18 because 8 plus 2, that's 10. I only need 5 electrons here. There, now we have 15 electrons. 2 in the first energy level, 8 in the second, and 5 in the third. That's 15 electrons. And they're orbiting. Yeah, Bohr said electrons orbit. I kind of answered these questions when I was drawing the models, but where Rutherford fell short was that he didn't have any idea where the electrons were located. Nope, he just said they're out there somewhere. Yep, that was it. Bohr, I mentioned this already, he said the electrons were orbiting the nucleus like planets around the sun. His key piece of evidence was the emission spectrum from the hydrogen atom. If you're not familiar with that, you might want to go back and review emission spectrum versus the regular light spectrum. Let me know if you have any questions about those two, because those are free game. But recall, he claimed that electrons were only allowed to be in specific energy levels, and that's kind of why he got the idea of the orbits. This question's on your study guide just to kind of help out with the following questions. But on the first thing you need to do with this one is label your energy levels. So I like to start off with this block, 1, 2, 3, 4, 5, 6, and 7. And then the second block starts with the number 2. Yep. So the second block, I lost my pen. Where'd you go? There you are. So 2, 3, 4, 5, 6, and 7. And then the third block starts with the number 3. So 3, 4, 5, and 6. And the fourth block starts with the number 4. 4, and 5. Then the second thing you need to do is it says place boxes around all 4 sublevels. I mean, if you want to color them in, that's fine. I did. So there's S, and I would go ahead and put an S there. There's the P block, so over there I'm going to put a P. There's the D block, so let's put a D. And last but not least, the funky F block. The previous question should make your life a lot easier to write the full electron configuration for uranium. Should not come as a surprise that I asked you to do the full electron configuration. Well, let's see. We have 1s2. That gets us through that. Then 2s2. That's through there. 2p6. Well, let's see, where do we go? That's all the way through that. 3s2. That takes us through there. 3p6. Gets rid of those. 4s2 gets rid of those. 3d10, reading left to right. 4p6. 5s2. 4d10. 5p6. 6s2. Oh, we should probably locate uranium. That kind of might be helpful. Uranium is right there, by the way. Okay, so we still have more to go. All right, 6s2. 4f14. Follow the atomic numbers. All right, 5d10. And you thought bismuth was a pain. 6p6. 7s2. 5f1. 1, 2, 3, and 4. Phew! Finally done with that. The orbital box diagram for the last sublevel. I'm not asking for valence electrons. I'm just asking for the last sublevel. Well, from uranium, our last sublevel was 5f4. How many orbitals are available in the F block? 7. So we need at least 7 lines representing boxes, because I don't like to draw boxes. 1, 2, 3, 4, 5, 6, and 7. You can draw boxes if you want. And I have to place all 4. So 1 up, 1 up, 1 up, 1 up. Oh, that's it. We're done. Write the shorthand electron configuration for potassium. Yeah, now I give you a shorthand, right? For something like potassium. Seems so unfair, I know. Well, you're going to back up the noble gas with a smaller amount of protons in it than potassium is argon. So we're going to start with argon. So potassium starts with argon. And let's see, 1, 2, 3, 4, 4s1. Yeah, that's it. Now I need you to draw the orbital box diagram for potassium's valence electrons. Just the valence. Well, let's see. From the previous slide, potassium was argon, 4s1. So I only need the 4s. One line, label it 4s with 1 up electron. And how many unpaired electrons does it have? Well, there's the 1, and it doesn't have a roommate, so it's all by itself, 1. Now for extra points, go back to uranium. How many unpaired electrons does uranium have? Let me know later. Which atom contains a larger 1s orbital? Well, this question kind of is asking about which one has a bigger radius. And if you recall, as you go down the periodic table, the atoms get larger because you have more orbitals and more electrons and more protons, which makes perfect sense. But if you did watch the video, your mind should have been blown. As you go this way, the atoms get smaller. Yeah. And there was a reason they get smaller. So first let's look at calcium and bromine. So here's calcium and here's bromine. So the correct answer should have been, who is larger? Well, that answer is calcium. And the reason has to do with 3 little words you really should know. Effective nuclear charge. Yeah, effective nuclear charge. See, and I'm not going to write all this down, but in general, the idea is the greater the nuclear charge, the more tightly, the greater the nuclear charge, the more tightly it draws in the orbitals. So calcium has a lower effective nuclear charge than bromine. Bromine has a greater nuclear charge. So bromine is more able to draw all those orbitals in more tightly because it has a greater nuclear charge. Calcium's nuclear charge isn't as big, and so calcium is bigger. It's like it's all puffed out. There's nothing really holding it tightly together. And this picture just illustrates what I was trying to say, but without using actually calcium or bromine. Here, the effective nuclear charge of lithium is 1.26, but neon is 2.52. Neon is much more able to draw these electrons in, or rather these orbitals in, and lithium doesn't do it so well. So lithium is actually larger than neon. In order to answer this question, you need to understand an ionization energy trend. Who is the greediest, stingiest, doesn't want to let go of electrons atom on the periodic table? Who is it? Well, if you guessed fluorine, you would be correct. This guy has the highest ionization energy. Well, you could make a case that helium does, but these guys don't play chemistry games, so we're not even going to worry about those guys. It's fluorine. And the closer you get to fluorine, the stingier it gets. These guys want electrons. If you recall, ionization energy is the energy necessary to remove an electron. Fluorine has no interest in losing electrons. It's all about gaining electrons. So if we want to arrange these in quarter, that's a good word, yeah, in order of increasing. So we're going to start with small ionization energy, and we're going to go to large ionization energy. So the smallest one on the periodic table is this one. The closer you are to francium, the more likely you are to lose an electron. The atom's like, here, take it, I don't want it. Okay, so who do we have? We have cadmium, so we better find cadmium on here. CD. Yeah, it's getting late. CD's right there. We have fluorine already circled. Cesium. Phosphorus is over here. Chlorine. And silicon. There we go, there's silicon. Okay, so who has the smallest? Well, that's cesium. Cesium's smallest, it's closest to francium. It's like, oh, take me away, don't want you at all. Alright, so cesium has a smaller ionization energy than cadmium. Yeah, both of these guys like to form cations. They're more than willing to give away their electrons. And then the next one, alright, so we got rid of cadmium, we got rid of cesium. Who's next? Well, silicon. Silicon, if remember, we can also draw the trend kind of like being a big diagonal that way. So silicon followed by phosphorus. Now you basically have to choose chlorine or fluorine. Well, fluorine is much smaller, so it's more able to hold those electrons tight. So it's chlorine and then fluorine. Okay, nuclear charge for this particular element. Nuclear charge. Well, what's in the nucleus of an atom? Protons and neutrons. Good. Those are both in the nucleus. What's the charge on a neutron? Yeah, it's 0, nothing. So the charge on the nucleus has to be the same as the number of protons. So if an atom has an atomic mass of 199 and it has 120 neutrons, how am I going to find the number of protons? Well, that's simple. We're going to subtract. So 199 minus 120, 9, and that's 79 protons. So who has 79 protons? It is gold. The nuclear charge, 79. I kind of already gave this answer away, I know. Well, let's write the symbol first. If you recall, the correct way to write the entire symbol for this is first we write the mass, and then we write the number of protons, and then we write the actual symbol. A long time ago, I gave you the generic form of A. From A is the atomic mass. And then below that, we had Z, which represented the number of protons, X. And this, of course, then was the symbol. And that is the correct way you should write it. The name of this, I already gave that away. It is gold. So how many valence electrons? Well, the best way to do that is we should probably at least write the shorthand configuration. So we're looking at gold, and we're going to back up to xenon. So Xe, and after Xe we start here. So that's 1, 2, 3, 4, 5, 6s2. And now we got to go down here to 4f14. Then we have to come back up here, 3, 4, 5, d9. The number of valence electrons we get from the s and p orbitals only. So, valence electrons, 2 valence electrons. To be honest, gold is one of those exceptions to the rule, but yeah, we're not really going to cover the exception, so you can just nod and smile if you hear somebody say, gold's an exception. You can go, yeah, my teacher said something about that. Don't worry about it. 6s2, 2 valence electrons. You do know the answer to this question, even if you're not sure about how I worded it, or how the textbook worded it is a better way to say it. Well, let's go back to the shorthand configuration for gold, which is right there. So we had xenon, 6s2, 4f14, 5d9. So what is the highest level of electrons reached? 6. So how many levels of electrons are occupied? 6. It has 6 energy levels, and it has electrons in all 4 sublevels, in S, P, D, and F. This cartoon just cracks me up. It is so cool. It demonstrates one of the awesome points of quantum mechanics, and I'm not really going to cover the point behind this cartoon. I'm going to leave you to mull this one over. It just cracks me up. But what I can tell you, make sure you understand the main ideas behind the quantum mechanics that we covered. You will be given a cartoon and asked to explain the main point behind the cartoon. And yeah, if you have any questions on this, or this cartoon you're just not seeing the main point, feel free to come and ask me. But I'd kind of like to see if you can get the answer to this one. And if you do, yeah, come see me for that also, because that's also worth points. That said, good luck on the test.